Hi students, I'm Kailash. In today's online class, I'll be teaching you Ohm's law in microscopic form. So state and explain microscopic model of Ohm's law, or state and explain microscopic model of current. So both are same. So state and explain microscopic form of Ohm's law, or state and explain microscopic form of current. Now, in 12th standard Tamil Nadu Samachir book, you don't have the statement of Ohm's law in microscopic form. So let me give the statement, you can make a note of it. Now, Ohm's law in microscopic form states that Ohm's law in microscopic form states that at a constant temperature, the current density is directly proportional to the applied electric field. So at a constant temperature, the current density, so in the earlier classes I taught you what is current density, isn't it? Current per unit area, that's what we call it as current density, right? So current density J, current density is denoted by J, is directly proportional to the applied electric field to the conductor, that is E. So this is what we call it as Ohm's law statement in microscopic form. So I will repeat once again. Ohm's law in microscopic form states that current density at a constant temperature, you have to start with the term constant temperature, is a very important one. Okay, so at a constant temperature, the current density J is directly proportional to applied electric field. Okay, so J is proportional to E. Now if I remove the proportional sign and I introduce a is equal to sign, so I have to multiply the right hand side by a constant, you know that. So here the constant is none other than sigma. Sigma into E. Now the constant sigma, the constant of proportionality sigma is called conductivity. So conductivity of the material of the conductor through which current is passed. Now the constant, when the term sigma will be a constant if and only if the temperature of the conductor remains constant. So that's why in the statement we use the term constant temperature. So at a constant temperature, current density J is directly proportional to the applied electric field. That is J is equal to sigma into E. The sigma is the constant of proportionality called conductivity of the material of the conductor. Now if I take E to the left hand side, I get J by E is equal to sigma. That is J by E should always be a constant. The ratio of current density to the applied electric field should always be a constant. The ratio of current density to the electric field will always be a constant sigma if and only if the temperature of the conductor remains constant, or else it will change. So the temperature varies and sigma will vary. If sigma varies, then the ratio J to E won't be a constant. If the ratio of J to E is not a constant, then I can't say J is proportional to E. So then Ohm's law in microscopic form becomes invalid. So that's why in the statement we use the term at a constant temperature. It's a very, very important term, what you should never forget. So I'll repeat the statement once again. At a constant temperature, the current density is directly proportional to the applied electric field. So this statement is called Ohm's law statement in microscopic form. So what I'm supposed to derive here is J is proportional to E. So this is what I'm supposed to derive. So we shall do it. It's very simple. Okay, it's an important paragraph question. So state and explain Ohm's law in microscopic form, or explain microscopic model of current. So both are same. So the way of asking the question, state and explain microscopic form of Ohm's law is state and explain microscopic model of current. Right. Now let me consider a conductor PQ. You know, all conductors are cylindrical in shape, a wire in fact. So all wires are cylindrical in shape. So let PQ be a conductor. Now let me connect the two ends of the conductor to a battery. So I have not shown the battery in the diagram. Let the right end of the conductor Q be connected to positive of the battery. Therefore Q will be held at a high potential. And let the left end of the conductor be connected to negative terminal of the battery. Therefore the NP will be held at a low potential. Now, so NQ is at a high potential and NP will be at a lower potential. Once when the potential difference is established or applied, current starts flowing through the conductor. And you know the direction of current is always from high potential to low potential. So thus current will flow through the conductor in this direction. And you know current is nothing but flow of electrons from one end of the conductor to another end. So once when the two ends of the conductor are connected to a battery, electrons will start drifting towards positive terminal of the conductor or positive terminal of the battery in fact. So the positive terminal would have been connected to the NQ. So the electrons will be drifting from the negative end of the conductor towards positive end because positive terminal will attract the electrons because electrons are negatively charged. So the electrons drift from negative end to positive end. So the dot what you see here is an electron. It will drift from P to Q with a drift velocity equal to V sub D vector. And you know drift velocity will always be opposite to the direction of current flow. Okay, fine. So this is the drift velocity of electron. Now let me consider an infinitesimal volume in the conductor. A small elementary cylindrical portion in the entire length of the conductor, infinitesimal portion of a conductor. So since the volume of this portion is very, very small, I am going to call this portion as volume element. So let me consider a small elementary portion, a small cylindrical portion of the entire length of the conductor. So the entire length of the conductor, a small elementary portion choose panniku. Its volume is going to be infinitesimally small. Therefore, I am going to call this portion as volume element. Okay. Let the length of this portion be dx. Let the electron, you know, electrons are going to drift from left to right. When the electrons drift from the NP to NQ, they have to travel all along the way by a distance equal to dx through the volume element. So let an electron drift through this particular portion, through this volume element and covers a distance of dx in a time dt second. Let me assume. So when the electrons are drifting from NP to NQ, they have to cross this volume element of length dx. So what the electrons are doing is, the electrons are going to drift through this volume element with a velocity v sub d vector and they are going to cover the distance dx in a time interval of dt. Let me imagine. Let n small n be number of free electrons per unit volume of the conductor. Unit volume means 1 meter cube. So if I choose 1 meter cube volume of this conductor, I can find n number of free electrons. So what will be the number of electrons in 2 meter cube volume of the conductor? In 1 meter cube, that is in unit volume, there are n free electrons. Therefore, in 2 meter cube, there will be 2n free electrons. In 5 meter cube, there will be 5n free electrons. Okay, right. Now, so my aim is to prove J is proportional to E. So that is what we mean by microscopic form of Ohm's law. Right. So what is that I am going to do is to derive J is proportional to E. First of all, I am going to derive relationship between current and drift velocity. So I am going to derive an expression which will have current in the left hand side and drift velocity in the right hand side. Or in simple words, I am going to derive a formula for current in terms of drift velocity. And from then on, I will be proving J is proportional to E. It's going to be quite simple. Okay, so how to express, how to derive a formula for current in terms of drift velocity? Okay, you know current I is given by rate of flow of charges. So dq divided by dt. So what is that I am going to do is, I am going to find quantity of charge dq flowing through the volume element in a time interval of dt second. So what is that I am going to do is, I am just going to find the quantity of charge dq, that is going to cross this volume element in a time interval of dt second, and preferably the quantity of charge dq what I am going to find should be in terms of drift velocity of the electrons. So I am going to find dq in terms of drift velocity of electrons, and I will be substituting it over there. So on simplification, I will end up with an expression which will relate current and drift velocity. So I'll have current in one particular side of the expression and drift velocity on the other side of the expression. So that's what I mean by relation. Okay, so we shall start doing. So what I'm going to do is, I'm going to find quantity of charge dq that is going to cross this volume element, the infinitesimal portion of the conductor what I have chosen. So shall we do it? It's quite simple. Okay. So first of all, how to find charge? So already you know law of quantization of charge. The charge carried by a body will always be equal to number of electrons lost or gained multiplied by charge of an electron. So charge is always equal to number of electrons multiplied by charge carried by an electron. So step 1. Find number of electrons that are going to cross this volume element. Number 1. Step 2. Multiply that result what I get with E, so that I will end up with quantity of charge that crosses the volume element in a time interval dt. Okay, right. So we shall first find number of electrons in the volume element. We know n is the number of free electrons per unit volume. So if I take 1 meter cube volume of the conductor, there are n number of free electrons. So if I know how many meter cube will be, that is how much will be the volume of this volume element, then it will be possible for me to find number of free electrons in the elementary portion of the conductor what I have chosen. So let me first find volume of this elementary portion. Okay, right. Listen, so volume of the elementary portion, that's what I'm going to call this elementary portion as volume element. So you can call it as a volume element, or you can just put it as elementary portion. So volume of the elementary portion chosen in the conductor. We can see it's a cylindrical, you know all conductors are cylindrical in shape. So the volume element or elementary portion what I have chosen is also cylindrical in shape. Now what is the formula to find volume of a cylinder? It's pi r square into h. So pi r square is nothing but area of cross section of the cylinder. So let A be the area of cross section of the conductor. So instead of pi r square I can put A, and h is the length or height of the cylinder. Here I am going to find volume of this elementary portion. The height or length of the elementary portion is dx. So A into height of the elementary portion is dx. So A into dx is going to give me volume of the elementary portion what I have chosen. Okay, so volume of the elementary portion is equal to A into dx meter cube. So in 1 meter cube how many electrons are there? N number of free electrons are there. In 2 meter cube, how many free electrons will be there? 2 times n. So in A into dx meter cube, how many free electrons will be there? N into A into dx. So if I multiply the number of free electrons per unit volume with the volume of the conductor or volume of the elementary portion, I will end up with number of free electrons in that particular portion. Right? Therefore, number of free electrons. So number of free electrons in the volume element is given by n into A into dx. So A into dx is the volume of this elementary portion in meter cube. N is number of free electrons per unit volume. So next let me find how much charge is crossing this volume element. எவ்வளவு charge in the volume element dt secondல cross பண்ணுது. We will find it out. So how do you find quantity of charge? You know, quantity of charge is always equal to number of electrons multiplied with charge carried by one electron. So n into A into dx will be the number of electrons crossing this volume element. So if I multiply this many number of electrons with charge of one electron, I will get quantity of charge crossing the volume element in dt second. Okay, right. So therefore, quantity of charge through the volume element, quantity of charge through the volume element is given by, so let me take it as dq. Since the elementary portion is of very small volume, the number of electrons crossing in a very small interval of time is also going to be small, and hence the quantity of charge crossing the volume element is also going to be very small. So dq is equal to n into A into dx into E. I have to multiply this with the charge of an electron. So let me write like this. So take this as number 1. So successfully I have found quantity of charge that crosses the elementary portion. Now but what I need is I have to express dq in terms of drift velocity. In the dq own expression I need to have drift velocity of the electron v sub d. So how to do that? Right. See, we know that velocity is equal to distance covered divided by time taken. So here the distance what the electron covers while flowing through this elementary portion is dx. And the time interval what it takes to cover this distance is dt. So if I divide dx by dt, I will end up with the velocity of the electron, which is nothing but drift velocity. Therefore, v sub d can be written as dx by dt. So this implies dx is equal to, on cross multiplying, I get v sub d into dt. So take it as number 2. So what I'm going to do is I'm going to substitute 2 in 1. Okay, so therefore I get the quantity of charge dq flowing through the conductor is given by n a e into, instead of dx, let me put vd into dt, v sub d into dt. So number 3. So successfully we have found amount of charge that is going to cross through the volume element. We know that I is equal to dq over dt. We know I is equal to dq by dt. Isn't it? Right? So let me substitute 3 dq over here. Or you can do like this also. You can rearrange this. Equation 3 can be rearranged. I can bring dt to the left hand side and I can get the result directly. So however you can do, it's your privilege. Okay. So this implies I is equal to, instead of dq, n a e v sub d dt. So this is your dq divided by dt. So dt cancels off. So hence I end up with I is equal to n a e v sub d. So thus successfully I have found the relationship between current and drift velocity. So from this I have to evaluate further and I have to reach the destination J is proportional to E. Okay, now before doing that, N, A and E, all these terms are constants. So if I remove the constant from the expression 4, I can conclude current flowing through a conductor is directly proportional to drift velocity of the electron. So current and drift velocity are directly proportional to each other. So current and drift velocity are directly proportional to each other. I is proportional to V sub D. So this is the conclusion what we can come from equation number 4. Right. Now let us evaluate further and reach our destination. That is J is directly proportional to electric field. So for which, first of all, I should modify this expression, or other words, I can say I have to relate current density and drift velocity. So now we have got a relation between current and drift velocity. So now what I'm going to do is I'm going to simplify this, rearrange this so that I end up with the relationship between current density and drift velocity. Right. You know, current density is the ratio of current to area, or current flowing per unit area is called current density. So current density J is equal to I by A. You know this formula. Current density J is equal to I over A. So rearrange equation 4 or take A to the left hand side so that I get, so from 4. So taking A to the left hand side, I get I divided by A is equal to N into E into V sub D. I by A is nothing but current density J. So J equals N into E into V sub D. So this is the expression number 5. So expression 5 gives me the relationship between current density and drift velocity. So again, N and E are constants. Whenever I remove constant from an equation, the equal sign changes to proportional sign. So I can end up with J is proportional to V sub D. So thus both current and current density are directly proportional to drift velocity of the electron. So this is how current density and drift velocity of electrons are related. Is it clear? Right. So more the drift velocity of electron, more will be the magnitude of current. Lesser the drift velocity of electrons, lesser will be the magnitude of current. And the same thing is applicable for current density also. Now, my destination is J is proportional to E. So that is what we mean by Ohm's law in microscopic form, isn't it? So how to deduce J is proportional to E? So we have got an expression J equals to N into E into V sub D. So how to do that? How to reach my destination? Okay. So already in earlier online classes, I have taught you, we have separately derived an expression for drift velocity of an electron. We have separately derived an expression for drift velocity of an electron. I hope you would remember that formula. No problem, I'll write it over here. We know that drift velocity of electron, V sub D, is given by E m by tau into capital E. E stands for electric field. Electric field always acts from positive charge to negative charge. So once when I connect a battery between the two ends of the conductor, an electric field will be established inside the conductor from positive to negative. Okay. Now let me put this in vector form. So drift velocity is a vector. So put a vector symbol over it. So E, m and tau, these are all scalars. E is the charge carried by electron, m is mass of an electron, and tau is average relaxation time, or average time taken for two successive collisions of an electron, okay, with the positive ions of the conductor. Fine. And E stands for electric field. So these terms, E, m and tau, they are all constant. I'm sorry, they are all scalars. And E is a vector. So let me put a vector symbol over here. And you know, charge carried by an electron is negative, so minus. Okay, so let me take this number 6. Let me first write expression 5 in vector form. So in vector form, so J, so whichever quantity is a vector quantity, you put a vector symbol and write. So that is what we mean by vector form. So an expression without vector symbol is magnitude form. Any expression with vector symbol over the respective vector quantities is called vector form. So J vector is equal to N into E into V sub D vector. n and e are scalars. Drift velocity alone is a vector. So let me take this as number 6 and let me take this as number 7. Now what I'm going to do is I'm going to substitute the expression for drift velocity vector, that is 7, in 6. Okay. So substituting 7 in 6. Okay. So I get j vector is equal to, let me keep n and e as such. Instead of vd vector, let me substitute minus e m by tau into e vector. So I get j vector is equal to n into e into minus e into m divided by tau. So these are all scalars. Let me simplify this. I end up with minus n e square m by tau into e vector. And if you look at all the terms within the brackets, n, number of free electrons per unit volume, it's a constant. Only when we change the material of the conductor, it will change. And E stands for electron charge, which is always going to be a constant. M is mass of an electron, which is a constant. And tau, average relaxation time, or time taken for two successive collisions at a given temperature, is going to be a constant. When the temperature remains constant, tau will also remain constant. So let me assume the temperature is constant. That's what I told you already when I stated this Ohm's law, right? Okay, so all these terms are constant. So keeping the negative sign as such, what I'm going to do is I'm going to replace n e square m divided by tau with a single letter. With a single letter. So what is that? With a single letter, okay. Fine. That's the thing. So j vector is equal to minus. So n e square m by tau is replaced with a single letter sigma into e vector, where sigma is called conductivity of the material of the conductor. We'll see what is conductivity a little later in the next online classes, okay? Right. So conductivity is a constant called conductivity. Now generally, by convention, we take the current density direction along the direction of electric field. So this is the direction of electric field. So we take the same direction of electric field as the direction of current density. Now whenever you write an expression in vector form and if you get a negative sign in the expression, it means the two vector quantities involved are opposite to each other. So as per this expression, j vector and e vector should act along opposite direction. But the thing is that current density will always act along the direction of electric field. Which means I should remove this negative sign from this expression so that it justifies j vector acts along the direction of e vector. So removing the negative sign. So since by convention current density acts along the direction of electric field, let me remove the negative sign. So j vector is equal to sigma into e vector. Now let me remove the constant sigma. So I end up with j vector is proportional to e vector, or in terms of magnitude. So let me take modulus on either side. So I get j is equal to sigma into e. So remove sigma. I get j is proportional to e. So thus the current density is directly proportional to the applied electric field provided the temperature remains constant. If the temperature remains constant, then the average relaxation time or the time taken for two successive collisions will remain constant. If there is any change in temperature taking place, then tau will change. If tau changes, then sigma cannot remain constant. It's no more a constant, it becomes a variable. If it becomes a variable, then j can never be proportional to e. So at a constant temperature, the current density is directly proportional to the applied electric field. So that's all about your microscopic form of Ohm's law. Okay, so thank you.